GMT is really an exciting thing because we know that over the last 400 years that telescopes have gotten bigger, and that has allowed us to see things with better detail and to see fainter things and to figure out what the history of the universe has been. Our technology for doing this is getting better and better. We're able to build big mirrors, and we know how to do this. We know how to build GMT. We know how to build its individual mirrors and put them together. We know that when you build a telescope that has a sharper view, and the GMT will have a view that is 10 times sharper than the Hubble Space Telescope. And when you build a telescope that collects more light, and the GMT will collect 100 times as much light as the Hubble Space Telescope does, that you are going to be able to do things that we can imagine and set out as our goals, to look at the history of the universe, how things have changed, find out more about the dark energy and the dark matter. Those are things that we know you can do. But I think the really exciting things will be things that we haven't yet thought of, that the new questions that will come. The other part that's really interesting about a big telescope on the ground is that you can change it. That is, you can change the instrument. So I think that even when we build the telescope, that won't be its final form. Those instruments will eventually be replaced by better ones that use the technology that's developed over the period from now to then. We know that the universe has changed from a very homogeneous kind of goo at the time of the Big Bang into a highly differentiated world where there are planets, stars, galaxies, clusters of galaxies. The universe has gotten kind of interesting and complicated through the action of gravity over time. We'd like to see how that works. And by looking at what happened long ago, which means looking at very distant, very faint galaxies, and looking in detail, which means having the resolution to kind of really see what's going on, two things that GMT will be really good at, we'll be able to trace the history of how matter has come together to form the stars and planets and galaxies that make up the universe today. But then there are a number of other things we want to know about the history of cosmic expansion. And on one hand, there's the dark matter. The dark matter is dark because it's invisible, doesn't emit light. And on the other hand, the dark energy, which we kind of made up so it would sound like the dark matter, and they are in a kind of tug of war in which the dark matter is trying to slow things down, the dark energy is trying to speed things up. And over the history of the universe, which we think is about 15 billion years, that the expansion of the universe has made the density of matter go down, and that means that the dark matter is getting weaker over time, that the gravitational tug is getting less, and the other stuff, the dark energy, which may be the cosmological constant or some other thing, has gained the upper hand. And so we've switched from a universe that was slowing down to a universe that's speeding up, and that switch, that change, took place, we think, about 5 billion years ago, about the time when the sun was formed. Then closer to home, the GMT will be fantastic for looking at individual stars in other galaxies that right now are kind of hard to measure. They're too faint for the Hubble Space Telescope, and you'll be able to analyze the light from those, see how the chemical history of galaxies has progressed. Well, one of the really interesting fields that's developed over the last 15 years or so is the study of planets around other stars, what we call exoplanets. It's kind of interesting because 20 years ago, there were none. What we'd really like to know is how many there are. We'd like to know, do all stars have planetary systems? Is a solar system a rare event or a common event? We know that lots of stars are binary, so there are two stars going around each other. What about those? Do they form planets or not? Now, after you've identified a star that has a planet around it by one of these techniques, then you really want to find out more about that planet. And it turns out that having a big telescope is very, very helpful because you gather information very rapidly because it has a big collecting area. And that means that you're in a position to find out things like, For example, if the planet crosses the disk of the star, you can measure the shadow, the diminution of the light of the star caused by this little planet going across. But you have to measure it all very rapidly because it's only going by for a short period of time where it's exactly in the right direction. So you need a big telescope in order to characterize these planets. We're interested, of course, in knowing whether there are planets like Earth around other stars. That's maybe a little self-centered, but we can't help it. We're really interested in knowing whether planets like Earth are very rare or common. I would say the lesson of what's been learned so far is that our imagination has been far short of what nature has actually done. That is, the things that we thought and the things we put in the textbooks and made people answer on the exams are actually wrong. That is, the simple idea that in our solar system, all the rocky ones are in the inside and the big gassy ones are on the outside, which seems perfectly sensible, and somehow the gas gets boiled off from the ones on the inside. That's what it always says in the books. It turns out there are other solar systems, other planetary systems, where those things are not true, and there are big planets like Jupiter in close. And what that means is our imagination is not good enough, and what we need is some facts. So that's why we need telescopes, because human intelligence and imagination and so on is not enough, that the universe is actually much weirder than we dare to think. And it's only when you get the information and you get the facts and you have the evidence that you're willing to even believe the things that are actually true. One of the more interesting things, of course, is to see if there would be some signature that a planet had life on it. And so it might change the atmosphere of the planet, just as living things on Earth have changed the atmosphere of the Earth so that it has oxygen in it. The fact that we have an oxygen atmosphere is the result of the metabolism of living things. So that's might be a clue, or there might be other clues, and people are really trying to think hard what we should look for. We don't know whether the most important things that GMT will do will turn out to be cosmological, sort of working at the great distances, or possibly having to do with planets, the formation of planets around other stars. We can have confidence that as we build the GMT, and we build other instruments that work in the radio and work in the infrared, that work in the ultraviolet and X-rays, all of these tools that we have, we'll begin to open a new set of questions that we haven't formulated just right at the moment, and that will let us kind of take the next step forward to really explore the universe in a better and deeper way.